Hi there, my single precision 32-bit floating point multiplier is just about complete. Most of it is done, just a couple of odds and ends to finish off. This is the top level here, and I'll just quickly talk you through it just to get an idea of roughly what it looks like. So we've got the input X here, so this is the input, and you can see that the input is in hexadecimal, so we've got 8 bits here for the hexadecimal, which represents the 32-bit binary input. And I've put it into a little RAM unit here. So it means I can sit here and I can just change the values directly at the RAM unit. And the same for the Y, I can change the values here. Or as I will do over the next couple of days, I'm going to run a test script on it. But I have to get a test script together for it. So that means I can load the test script here directly. So I'll create maybe a 256 different values, and I'll stick it in just to check and see that it's working correctly. This is a little counter here just to count in for the address for these RAM elements. And you get the final output here. Well, there's a multiplier here, so the X value and the Y value come in here, and then the final output comes out here, X times Y out, and then it goes into this ROM here. And you can see the output is given in the hexadecimal value here. And I've also got the flags here coming up. So I've got a not a number, I've got overflow to plus infinity, overflow to minus infinity, underflow to plus 0, underflow to minus 0. So let's go inside and we'll have a quick look at it and we'll see how it looks. So I've tried to keep the architecture as you would see maybe in a typical book with the block diagrams. So we've got an input X here and an input Y. We split the input into the sine, the exponent and the mantissa. So again, it's just a simple splitter there, and we just split it into the sine, exponent and mantissa. So nothing real interesting there, and the same for this section here. Now we have a section over here which I'll go over quickly. It's called type, okay, and it just works out whether the input is normal or subnormal. So it will have the input for X and input for Y. A normal will give a value of 1 and a subnormal will give us a value of 0. And it will also work out whether the output is going to be a normal or a subnormal from this little section here. So I'm not going to go over it in any detail, I'll just go through quickly so you can see roughly how it looks. So once we've worked that out, we come into the bias section here. So the bias section is either going to pass a value which is going to be the unbiased exponent minus the 127 if it's a normal input, or if it's not a normal input, it's a subnormal input, the bias will run through this route here, and it will generate the bias from the value of minus 126 minus a pre-leading 0 count. So you get the pre-leading 0 count from a different section. So basically what we do here is we take any subnormal number and we normalize it, and we count the number of leading zeros the original subnormal had, and we're able to use this value as the new unbiased exponent. So it either goes through this route here for normal, or it goes through this route here for subnormal. Now that's the same for the biasing for the Y, exactly the same circuit but just for the Y input. We then come out of this and we go through the summer here. Now there is just actually a simple input here for X and Y, and then the summer, then the output, but I've added on into this the overflow to plus overflow to infinity and the underflow to 0. It's not actually signed here, so we sign it at some other point through the circuit, but that's what we use here. We then head through the other two summers, which will give us the two paths here. So the path is going to be the EX plus EY plus B and EX plus EY plus B plus 1. And we make a choice of this path dependent on the 48th bit of the multiplication of the mantissa. And that's the choice here from that 48th bit. And it will choose either this one here or this one here. And we have the final output coming through. And if it's a subnormal output, the mux here will change that subnormal value for the exponent just to all zeros. So if it's a normal input, then it'll just come down this path here and down this path, or it'll come down this path and down this path here, depending on the 48-bit. So for that does for the summing of the exponents. For the multiplication of the mantissas, we head in here now. We got to, first of all, we've got to bit extend the mantissa. So it's either going to be an extension by a value of 1 for a normal number or 0 for a subnormal number, and we do this here in this little section for the bit extension. Now, another thing we do here is we pre-normalize any subnormal number. So we take a subnormal number and we shift it in order to pre-normalize it. So if it's just a normal number, the path it goes through is through here, down through here, and out through the multiplexer. If it's a subnormal number, the path it takes is through here, down through here, and then up through this shift right, shift left, and then through the multiplexer to do the pre-normalization. And we also get this leading zero count, which we've seen in the exponent section, and that's where we generate that from. So we get the exact same thing for the y value. It's the exact same circuit, and the multiplication happens here. So this is just a straight multiplication, and we take the 48th bit out here as our test bit for the rest of the circuit. We then have this shifting section here. So this shifts the mantissa by the correct value. So we're either going to shift the mantissa the decimal point left by 1, or we're just going to leave it remaining the same if we've got a normal output. But if we've got a subnormal output, then we're going to have the shift. Now the decimal place would be shifted left by that xe plus ye plus a bias plus 1. But that's a bit awkward to generate within Logisim here, so I've generated it a different way. Rather than left shifting the decimal point, we just right shift the entire mantissa by the bias, and it's a much easier way of generating it here. So we just right shift by the bias, and we get the new correct position for the for a subnormal output. And again, there's a choice here made from the left or the 0, left 1 or left 0 by the 48th bit. Now the choice for the normal output and subnormal output comes at the top level here. So whenever we come back down here, we've got another multiplexer here that's going to choose the normal. It's going to choose the normal or the subnormal output, depending on what we worked out within this type section. And that's going to feed down through here, down to this incrementer. Now we're also taking a copy of the output here of the lower 48 bits in order to use them to work on the rounding. Now the rounding is also shifted by 1 value here or a 0 value depending on the 48th bit. So we're really using this as a subnormal rounding injection. So we inject the rounding bit at the correct place. So there's only 1 digit difference here between one and another, but I thought I'd put it in just to get it correct. Now I've still to add the subnormal rounding injection. This is actually the normal rounding injection here we've got at the moment, but there will be another section here which will be the subnormal rounding injection, in which case instead of shifting this by just the value of 1, we're going to shift it by the value of the bias in order to get the correct injection for the rounding. So that's that section there. And if we head back up, we then go through and we take this correct value for the least significant bits. So we take the correct 23 least significant bits, and then we put them through the sticky bit, which is just an OR gate here. So we OR those all together, and then we go through the rounding section. Now the rounding section here, it takes the 23rd bit of the least significant bit of the 48-bit multiplication, and it also takes the 24th bit, and it takes the sticky bits which we've seen generated above with that OR gate, and it runs through this little table. So this is a little truth table for the rounding. The only ones that are interesting here are what happens whenever there's a tie. So in a tie in this instance here, if we have 1 and all zeros, then we look at the least significant bit of the first 23 bits of our multiplication, and if it's a 0, then we just leave it at 0. So that is, it just leaves it at that even number. And if we come down here, if there's a value of 1 here and all zeros for the sticky bit, or the rounding or sticky bit, then we will add 1 on, and this will, by adding 1 on to this will give us a value of 0, the least significant bit. So in effect, it has gone to the next even bit up. So this is a rounding to even. So we can see that we're, statistically speaking, we're going to have half the numbers are going to be even and half the numbers are going to be odd. So we're going to be half the time rounding up and half the time rounding down in order to get to an even value. So, and this is the little combinational logic circuit which generates this truth table here. And then we head on out to the incrementer. So if this gets incremented, you can see in this case it has actually been incremented, and that means that we add 1 on to the value here. So and of course, if by adding 1 on to the value of the mantissa, there's a possibility that that 1 could ripple all the way up through the mantissa into the exponent. So we cater for that by adding a carryout, and this carryout would be used in order to increment the exponent if it was required to do so. So in this instance here, we can see that we have a 48, bit 48 goes high, so we're going to take that 48 bit and it's going to make that choice here, and the increment in this case here hasn't rippled all the way up through to the exponent section. Now, a thing that tends to get lost here sometimes when people are building these, they put they have this going through 2 possible incrementation phases. So they might build it and have an incrementation for the 48th bit and also an increment for this counter here, but you'll only ever get one happening at once. The 2 of them won't happen at the same time, so you'll never have a double increment here of this exponent. There will only ever be one increment, and that is the basic idea. The only other bit I've got to show actually now is that we're going to have an x and y output, okay, but that's us just multiplying together the vast majority of numbers, but it doesn't take care of special numbers, for example multiplication by 0 or multiplication by plus and minus infinity or not a number. So those have to be taken care of in this section here for special cases. So if we have a quick look in here, now the way I've worked out this here is I created a Excel spreadsheet and put in every single combination of possible values that we could have for all of our special cases, and then I whittled the ones down that made no sense, and also ones that were repeated could have been were chopped away as well. So finally what I was left with are these here. So these are comparators. So what I do is we take the inputs for x and y and also the sign for the input, which is the very first bit of the 32-bit number, and we work out whether we've got a number here which is plus infinity for x. So plus infinity is this 8-bit number here, so that's the 8-bit hexadecimal that represents the 32-bit number. So if that's plus infinity for x and you've got plus infinity for y, and you've got plus 0 for x and plus 0 for y, not a number for y, not a number for x, and again minus infinity for x, minus infinity for y, minus 0 for x and minus 0 for y. So these are all the possible special numbers that can come in. Now the other option that we can have here with these is that we can multiply each of these by just a normal number or normal or subnormal number that comes in. So we can have a normal number for a positive x value, and a minus x value, and a positive y value and a minus y value. But in order to actually generate these numbers, we don't actually know what the numbers are because there's a vast sea of them, but we do know what the numbers are not, and they are not any of the special cases. So as long as we check and make sure that none of the special cases occur, then we can ensure that we get the correct value here for that plus x and minus x, plus y and minus y. Okay, so I wouldn't expect you to understand all of this just looking through it here like this. You'd have to go through the entire course in order to get a really good grasp of it, but it gives you an indication. Now, finally, the other two blocks here. So we take these comparator values and then we generate all of the possible outputs. So the plus infinity could be generated by these two, or it could be generated by these two, or these two, or these two, or these two, or these two, and the same for minus infinity, plus 0, minus 0, and the not an and can be generated by this lot here. Okay, and finally, when we head out to this last part of the special cases here, we're going to have our output here, which is their final output, but their output has been split. We've got the normal path that you would get via the normal multiplication of a normal or subnormal number, which would be through this path here. But then we have the other paths, which are the paths which would give us our plus infinity, minus infinity, plus 0, minus 0, and not a number. And we choose these values here depending on our little circuit here. Now I don't want to go through all the details of this circuit, but it will be in the course, and I'll go over every bit of it in minute detail. So you can see here that if I head up to the top section again, well, we've covered everything we have in here. Within this unit here we just have a concatenation, so we just join the three values here together to get that output there. So there's nothing else in there we want to talk about. The exclusive OR, I suppose it's quite straightforward. To get the sign, you exclusive OR the sign x and the sign y, and it just gives us that final output. So this here will multiply all normal times normal giving a normal, normal times subnormal giving a subnormal, normal times subnormal giving a normal, and normal times normal giving a subnormal. So it multiplies all of their number types together. Now at the top level here, you can see here that we could maybe just put in a simple value here. So I'll just put in not a number. So 7 F is not a number, and you can see not a number appearing. And if you're wondering what happens when you multiply not a number with not a number, it's hardly surprising you get not a number. So I won't show any more. I can mess about with this, and I can get all the different outputs that you expect to get, and I could check this, and you can see that these change, and there'll only be one coming on at a time. So in this case I've multiplied these two numbers together, and there's an overflow to minus infinity. So that's all there is for the multiplier section. There's a couple of things I have to add. Like I said, the correct injection for the subnormal rounding, and I'm also going to add in one other option here, one output of one flag, which will be a flag that's going to show us whenever the multiplication is an inexact multiplication. So there will be an inexact flag coming out here as well. And I'll probably take another output which will tell us whether the number types that we're multiplying, so normal times normal giving a normal, or normal times subnormal giving us a subnormal. So there'll be 4 of those, so I'll bring those out as well, and that'll do the multiplier, and that'll be all completed. The last thing I say I have to do is to generate a testing script for it, which is really I'll probably write a bit of C code and generate a load of values. I'll do two. I'll do a small one with maybe 256 values, and I'll do numbers that are at the junctions between the different number types, because that's where the problems can occur. So I'll do numbers that it's close to the largest normal number and heading off to infinity, and a set of numbers that go between the smallest normal number and the largest subnormal number, and I'll do a range there, and also the smallest subnormal number heading to an underflow to 0. So I'll get another set of numbers for that. And once I've done that and I see it's working okay, I will go ahead and I'll generate a larger script. So I think I can actually get up to about 60 meg of information in each of these. So I'll generate a larger script in C, and I'll find the actual floating point number, the correct representation within C. So I'll have a really clean data set to start with and use that as a test. And whenever I've got the output here, I'll take the output from the C multiplication file and the output from this file here as well. I'll stick them into Excel, and I'll write an Excel VBA script that'll make a comparison, and that'll give me a final check and see the veracity of the multiplier and how good it is and whether it is actually working exactly the way I'd like it to work. So that's all for this video. Don't worry if you're looking at this and scratching your head, because I would hardly expect you to understand all of it just from this quick introduction. If you really want to understand the whole of the multiplier, then the course will be coming on very, very soon, within the next week. So thank you for listening. I'll get you in the next video. Goodbye.